Question 42 says that the number of decibels D produced by an audio source can be modeled by the equation D equals 10 log I over K, where I is the sound intensity of the audio source and K is a constant. How many decibels are produced by an audio source whose sound intensity is 1,000 times the value of K? As answers, we have numbers ranging from 4 to 10,000, and answer choice H is 10 times answer choice F, and then answer choice K is 100 times answer choice J. In reading the question, there are a few things that stand out. ACT math concept-wise, we're working with logs. And the other thing that stands out is that they've given us these two letters, I and K, but they haven't told us values specifically for those two letters. They've only told us the relationship between them, which is that the sound intensity is 1,000 times the value of K. And noticing that, it suggests that one approach we can take to this question is that we can plug in values for I and K that satisfy that relationship in order to solve the question. And then the last thing that really stands out to me in this question is that the way that it's presented, it seems like it's deliberately been worded to seem pretty intimidating and abstract. So for one thing, there's all this mention about acoustic stuff with the decibels and the audio sources and sound intensity. And then there's also all these letters, D, I, and K. So all of that together can feel a little bit overwhelming. And it's helpful to keep in mind when we notice questions that look like this, that underneath all of it, ultimately the ACT can only test us on relatively basic math. And so inevitably, what we're going to find here is that it's just going to be basic math as it always is. And that leads to the approaches that we can take on this question, which I will write here at the top. So one is more concrete, which is basically to give examples for I and K and solve. And the second way is to use algebra to relate I and K and to solve it from there. So use algebra to relate I and K and solve. Either of these ways of approaching the question can be super efficient. As always, I'm going to start with a more concrete way just to reinforce our awareness here that we can use that approach on this test. So let's go back to what the question was asking us, which is how many decibels are produced by an audio source whose sound intensity is 1,000 times the value of K. And we were given that equation in the beginning that relates the number of decibels to I and K through this equation. And if we're going to use this concrete way of giving ourselves examples for I and K, we just need to follow the relationship that they've told us here, which is that the sound intensity, which we know is labeled with I, is 1,000 times the value of K. So let's just choose easy numbers to work with here. One thing we could do is we could say K is equal to 1, for instance, in which case I would be 1,000, because that's 1,000 times 1. Now, we just go to this equation and we plug in those values. So D is equal to 10 times log of 1,000 for I, and then 1 for K. And now we have 10 times log of 1,000. And there's a couple of different ways that we could simplify this. One is if we know how logs work, then we could just figure out that log of 1,000 is going to be 3. And so this would be 3 times 10, which is 30, and G would be correct. If we're not as comfortable with logs, we can also enter this expression into our calculator. And we do 10 times log of 1,000, and then just press enter, and it simplifies it for us, so we get 30 again. And as a brief note here, we chose 1,001, but we could have chosen any two values that satisfy that initial relationship where I is 1,000 times K. For example, if we had decided to choose like K equals to 2, then I would be 2,000. And if we were to plug that into our original equation, we'd have that D is equal to 10 log of 2,000 over 2, which that just simplifies to 10 times log of 1,000 again. And so we just get what we had gotten with the other example, and we'll get the exact same answer of 30. Let's now look at the second approach, which is to use algebra to relate I and K. And with this approach, we're not going to actually plug in numbers for I and K. We're just going to create an algebraic equation involving them, and then we'll take it from there. So we know again that the sound intensity, or I, is 1,000 times the value of K. So we can just write that I is equal to 1,000 times K. And then we can go back to that equation that D is equal to 10 log I divided by K. And we can just substitute in this I value, which is the same as 10,000 K, in for the I value here. So this is going to be the same as 10 times log of 1000 K divided by K. And these K on the numerator and denominator will cancel out. So this becomes 10 log of 1000, which, as we've seen in the previous examples here, simplifies to 30. So we end up getting the same answer. Let's look at a couple of these wrong answers now. Answer choice F of 4 could reflect a mistake in either of these approaches of including this 10 outside of the log inside of the parentheses. Because if we multiplied that 1,000 by 10, then the log of 10,000 becomes 4. Answer choice H might reflect a similar mistake since it's just answer choice F times 10 again. Answer choice J of 100, I'm not sure what that's anticipating, but answer choice K of 10,000 could reflect a mistake in trying to simplify the log, and instead of getting that the log of 1,000 is 3, getting that it's 10 to the third power, because then if we did 10 to the third times 10, that would lead to 10 to the fourth, which is the same thing as 10,000. And now I'm going to write out what we ultimately needed to know on this question right here, ultimately needed to know. And it really turns out that we didn't need to know pretty much anything as long as we chose a value for I and K, where I was 1,000 times K. We just literally plug this into our calculator and solve it. So I'm just going to say we kind of needed to know nothing for this one. That being said, we do want to have a basic familiarity with how logarithms work and how we can set up equations from logarithm expressions, because on some ACT math sections, we'll be expected to know sort of the basics of logarithms, and we won't be able to use our calculator to solve them as easily as we did on this question. So I'll link to some resources in the description that go into further depth about logs. As far as ultimate takeaways from this question, now that we've solved it, we can see in retrospect that, as we expected, the math underlying it was relatively basic. In fact, we didn't need to know much at all to get the question right. And now we can really see much more clearly what the ACT was up to in writing it. And in fact, it's very clear that they're up to their old tricks of using abstraction with all these different variables going on, as well as using intimidating language and presentation of the question to kind of make the question more difficult. So that's really where the difficulty of this question is just in the presentation of it. And that's a common theme that we've seen many times and that we'll continue to see on the ACT math. And in solving the question, we saw that one of the most helpful tools in combating all of this abstraction is to make things concrete again. So when they give us variables like this, we can just give ourselves numbers. For other examples from this particular test where we can give ourselves examples like we did here, check out questions 16 and 27 because they involve a very similar approach. That wraps things up for question 42. Let's go on to 43.